Welcome to Rust, a systems programming language renowned for its focus on safety and speed. It offers memory safety without needing a garbage collector and boasts a powerful concurrency model. As Rust rapidly gains popularity, it's being chosen increasingly over C and C++ for modern software development due to its innovative features, such as the ownership model, which eliminates many classes of bugs. Let's explore what makes Rust the future of safe systems programming. Having introduced Rust's foundational strengths, let's delve into the unique challenges faced by C and C++ developers when transitioning to Rust. A primary hurdle is adapting to Rust's strict ownership model, a paradigm shift from the manual memory management often experienced in C and C++. This model enforces rules, ensuring safe memory access and preventing data races at compile time. In contrast, traditional languages may require intricate manual checks. Mastering these concepts is crucial for leveraging Rust's full capabilities. Building on Rust's innovative ownership model, let's explore the essential syntax elements that distinguish Rust from C and C++. We'll start with variable declarations, where Rust enforces immutability by default, requiring explicit mutability tags. Notice the similarities in basic data types, but appreciate Rust's stricter type safety. Control structures like if statements are reminiscent of C++, providing a familiar yet robust experience. We'll demonstrate this through concise code examples to solidify your understanding. Now that we've explored Rust's syntax basics, let's dive into a live coding demonstration. We'll bind variables, utilize a simple loop structure, and define a function. Watch how Rust's syntax elegantly handles these tasks with both efficiency and clarity. Observe the execution as we iterate through a loop, updating a variable, and perform addition using a custom function. This demonstration highlights Rust's straightforward yet powerful approach to common programming patterns. In the live coding demonstration, we witnessed Rust's syntax in action. However, when writing Rust code, developers often encounter common errors, particularly with borrowing and lifetimes. Rust's ownership model enforces strict rules to ensure memory safety, but misunderstanding these concepts can lead to compilation errors. For instance, simultaneous mutable and immutable borrows lead to conflicts, as shown in our example. Always remember that Rust requires precise lifetime annotations to resolve such issues. Adopting best practices, like consulting the Rust documentation and using the compiler's guidance, can significantly mitigate these challenges. Throughout this tutorial, we've explored Rust's core syntax, highlighted differences and similarities with C++, and examined common pitfalls such as borrowing and lifetimes. By understanding Rust's ownership model and practicing with the provided code snippets, you can enhance your proficiency and avoid common errors. Remember, Rust's focus on memory safety is a powerful advantage. We encourage you to share your experiences, ask questions, and continue to engage with the coding community in the comments. We look forward to hearing from you.